In this video, we are going to derive the formula for area of ellipse, which is a lot easier, and also for circumference of ellipse, which looks a bit complicated. Yeah, though we might not expect it to be, but it is. Okay, now let's get on to deriving these formulas. But before we go to these formulas, I will just recap some of the ideas about ellipse that we know. Okay, so basically, in ellipse, it looks like an extended circle, and it's symmetric about both y-axis and x-axis. We have a semi-major axis A, and A is supposed to be longer than semi-minor axis, which is B, and we have a directrix over here. Yeah. And basically the role of, and also we have a foci over here and here. These are foci. And if we have a point and circumference, and basically the special thing about ellipse is like taking random point on circumference of ellipse, and wherever the point might be, PC dash plus PC is always constant, and this is one of the definitions of ellipse as well. This is always constant. And the other definition of ellipse goes like this. If this line directrix is L, PC over PL is always constant, and this is known as eccentricity of ellipse. Or for any conic, it holds. Like distance from a fixed point by distance from directrix is actually the eccentricity of conic section, and also for the ellipse. And some of the other formulas for eccentricity of ellipse is also that it's C, this length C, over this length A. So this is A, and this is C. Okay, so eccentricity is also defined as C over A. This can be found by some simple manipulations of this original formula. And after we have C over A, we also have other formula, for eccentricity. For that, we first need to derive that in ellipse, A square is equals to B square plus C square, where B is semi-minor axis, A is semi-major axis, and C is the length from center to focus. Okay, to derive this, we can just join these points. Okay, and let this be P dash. And since this is isosceles triangle, both of PC and PC dash will be equal. Yeah, so we have P dash C. Okay, so these two are equal. So we have P dash C, 2 times P dash C. 2 times P dash C, and this length should be equal to. If let's say take another point over here as M, MC dash plus MC. We can do this because of the definition of ellipse, right? So we have 2 times P dash C equals to MC dash plus MC. Now MC dash is just A plus C, and MC is just A minus C. So this is actually 2A. So we get that P dash C is actually A, it's A. Yeah, so P dash C is A, and now from Pythagorean theorem we can see that A square equals to B square plus C square. So if we have this, we can also change the formula for eccentricity of ellipse as following. It will be C will be now root under A square minus B square over A, and we can change this as root under 1 minus B square by A square, which is an alternate formula for eccentricity of ellipse, and it's used quite often. So after we have known about eccentricity formula, the other thing that we need to know is the parametrization of ellipse. Okay, so basically the formula for ellipse is let me just this. Okay, so the curve of ellipse is described by this formula: x square by A square plus y square by B square equals to x. Now A general point that satisfies this formula can be x equals to a sine theta and y equals to b cos theta. So if we have these two general forms, if we substitute here, we have sine square theta plus cos square theta, so that's equals to 1. So, so for any point on the ellipse can be obtained by this parameterization. A sine theta comma b cos theta. Okay. So this parameterization a sine theta comma b cos theta can help us to get the points on the ellipse. Yeah. Okay. So with this, we are ready to begin these integrals, deriving these integrals. First one for area is a lot easier. It's not that hard. So we have this ellipse. We have A, B, we have center, and the equation of ellipse is x square by a square plus y square by b square equals to 1. Yeah. Now if we want to find the area of ellipse, we can just first find the area of 1/4 and multiply by 4 since it's symmetric toward y and x axis. To find the area of the 1/4, we can just have integral from 0 to a. Yeah. And this height times dx, height times dx, height times dx, we can do that. Okay, so it's x, this is y axis. We can do that. And now for height, we can just get a formula in terms of x from this equation. We have b square. So I guess it will be 1 by b root under 1 minus x square by a square dx. So the expression for y comes to be that one, you know? Y square b square equals to 1 minus x square by a square, and then y equals to b times root under 1 minus x square by a square. Yeah, we have that. And now for this one, we can use standard integration ideas. Yeah, so we can first take LCM, a by b. Yeah. Okay. So this will be a square minus x square. We will have 1 by ab. So 1 by ab integral from 0 to a root under a square minus x square. Is it? No. Actually, we have over here b in the numerator itself. So I had made a mistake. I'll correct it. No. Now it's find b over here, b in the top. And now to integrate this, again just either as visual representation or like go by standard formulas. So standard formula of this form is x by 2 root under a square minus x square plus x square by 2 sine inverse x by a. To derive this, you can use trigonometric substitution or just remember this formula. Okay. And then if we evaluate this integral at the required limits, we get b by a. This will be 0 plus a square by 2, sine inverse 1 is pi by 2, and minus 0 minus 0. So this is a and a cancel out, so pi ab by 4. So pi by 4 is the area of 1/4. So the overall area of ellipse will be pi ab by 4 times 4, and so the area of ellipse is pi ab. This is how we derive the formula for area of ellipse. Now let's move on to the circumference of ellipse. Okay. For it's rubbish section. Yeah. So for circumference of ellipse, we have this whole length as A. We have a foci over here, C. So we have a focus and foci as plural, and then over here B. Okay, I don't need directrix right now. Okay, that's fine. Okay, now for circumference, we'll just find circumference for one quarter, only this length, and multiply by 4. Yeah, since these are the symmetric. And to find this length, we know that when we are like finding the length over a curve, when we're finding the length of a curve, we just integrate in our required domain, root under. We just integrate actually this dl element over here. Yeah, this is x, y. So we just integrate these dl elements, dl elements, and so in this very small part over here, if this is dl, and we have a dx in this thing, dx over in this direction and dy in this direction. Yeah, so dx and dy, and we can see that dl is actually root under dx square plus dy square. Yeah, so we will just integrate in the required domain, root under dx square plus dy square. So this is the formula for finding the length of curves, and so we'll use that here over here as well. So we are integrating from 0 to a. Okay, so 0 to a, root under dx square plus dy square. But I cannot actually say 0 to a since we don't have any single the variable, like main variable of integration. I'll just for now I can just say in the required domain, root under dx square plus dy square. Yeah, this will be the formula. Now we can just use the parameterization for simplifying things. We know that x equals to a sin theta over here, and y equals to b cos theta. Yeah, and now we get this curve when theta runs from. Okay, so theta runs from 0 to pi by 2. Actually, for x equals to 0, we get this point over here. Since x is 0 and y is b, so we get 0 comma b, which is this point over here. And it would be better like if I just change this parameterization as x equals to a cos theta. Yeah. Anyway, it works. It just gives the curve, but this one will be more nicer, b sin theta. Because for theta equals to 0, it gives this point over here. Yeah, this point. Theta equals to 0, we have a comma 0, so which is this point. For theta equals to like 30 degree, it gives a point over here. In 90, it gives point over here since cos 90 is 0, x is 0, and y is b. So we get this point over here. So as theta ranges from like 0 to pi by 2, we get points on circumference. Yeah, so we'll basically use this parameterization as this is more helpful for just running in integral cos direction. And this also works later. Okay, so now use this parameterization, and for finding this length, theta will go from 0 to pi by 2. So integral from 0 to pi by 2, we can now do something like pi by 2 root under dx by d theta whole square plus dy by d theta whole square times d theta. Yeah, we have just multiplied and divided by d theta square, d theta. And now I don't think it's a lot harder now. We can have 0 to pi by 2. Dx by d theta will just be now minus a sine theta, and when squared, it's a square sine square theta. And the other one will be b square cos square theta times d theta. Now we can just change sine square theta into cos square theta. And before that, we can first take out a as common, and we will have sine square theta plus b square by a square cos square theta. Yeah, and again we can change this. So we will have 1 minus cos square theta plus b square by a square cos square theta. Is it? Yeah. B square by a square cos square theta d theta. And now what we can do is a times integral from 0 to pi by 2 root under 1. And now if we just take minus common over here, we will have 1 minus b square by a square, and then cos square theta d theta. D theta is not inside the root, eh? Just some typo things. I'm so sorry for that. I should better erase it, I guess. Yeah. Okay. And then d theta. So we have this to common, you know? We have just to minus cos theta as common. Now this is just e square. So we have a times integral from 0 to pi by 2 root under 1 minus e square cos square theta d theta. Yeah. So now our formula is actually formula as sine theta. Okay. So for that, it's actually the same thing, like whatever we get. And we can also get into that formula by using the fact that integration from a to b f of x dx is actually equals to integration from a to b f of a plus b minus x dx. This is known as King's rule, and by using this thing we can get into our required formula. You know? A integration from 0 to pi by 2. So in the place of theta we can use pi by 2 minus theta, yeah, and that gives us sine theta. So we have 1 minus e square sine square theta d theta. So this is the length of arc for only one quarter, and the ellipse for only this first quarter, and for all 4 quarters we need to multiply this by 4. So we get the circumference of ellipse to be 4 times a integration from 0 to pi by 2 root under 1 minus e square sine square theta d theta. So this is how we derive the formula for circumference of ellipse. I hope you got it. I had already described this was e square. We also know these things, and now I don't think there's anything harder that might hamper your understanding. Okay, so we have derived these both formulas, and we were surprised to find that there wasn't any nicer form for circumference of ellipse. And yeah, this is it. Keep enjoying maths, keep deriving things, and enjoy the beauties of nature. Thanks for watching, and look forward to seeing you in the next video. Thank you.